humans come on the scene? Well, this is the 800-year record of carbon dioxide. And you can see it's fluctuated a good bit through these glacial cycles. But you can see that carbon dioxide has generally ranged in 800,000 years somewhere from around 180, roughly, parts per million up to around something under 300. And right about here is when we had our industrial revolution in the middle 1800s, and now it's actually above this chart. It's 410. So our carbon dioxide in the atmosphere now is significantly higher than it's been in 800,000 years. And during this 800,000 years, sea level has fluctuated about 500 feet. So it would suggest that we're in for a ride, right? I mean, this can be a little scary when you think about it. Now, where did humans come in on this scale? Well, roughly, there's a lot of discussion about that now, but somewhere several 100,000 years ago is probably when the first humans, modern humans, came on the scene. About 100,000 years ago is when they started migrating from the area in Africa around Ethiopia, where they think they, basically originated. And probably 50, 60,000 years ago is when they made it up into Europe. By the time they made it over to Alaska, that was about 15,000 years ago. And by the time they made it down here to the southeast in what's now Georgia, was probably 13,000, 14,000 years ago, something like that. So it's basically a little blip here at the end. Humans were here. This was way before humans were on the scene. So we can't blame any of this on humans. That's natural. Okay, go ahead. This is the last 24,000 years ago, and I start this. This was when we had the last glacial maximum right about in here, around 20 to 22,000 years ago. Notice what sea level was at that time. That's what's plotted here. Sea level at that time was about 125 meters below what it is today. That's roughly 400 feet. So sea level was 400 feet lower than it is today, and it's been coming on up. Now notice around the time of the Great Pyramids, which would have been somewhere right about here, from then till today, it's been pretty constant. Sea level has been pretty steady during that period, which has probably enabled civilization to prosper. They didn't have to keep running up the hill to get away from the rising sea level. Okay, go to the next one. But what's happened since then? So since the time of Industrial Revolution, essentially, which was about the mid-1800s, we've had this steady increase in CO2 and associated with that steady increase in global temperatures. And then we've had recent sea level rises, also about the same time frame. Started in the 1880s, we've had steady increase in sea level as well. Is it just by chance? Probably not. Okay, Ted, let me go to the next one. Now, some of you might say, well, there was natural causes going on. We had this variability in solar intensity, and we've had orbital changes. We got all this other stuff we can blame it on. Well, if you actually look at it, and we've kept pretty good records of what's happened with the sun, this is the solar output that we've received. You can see the sunspot cycles pretty effectively, but if you look at the scale, this change is very, very small. And we can account for that. But this is what's happened with the global surface temperature. During this period from the 70s to today, it's continued to increase. From about, the difference was 0 here at the beginning, and now it's about, at least 1 degree or more above what it was. Okay, Ted? Now let's go ahead and think about sea level rise and what it's due to. Well, it's basically due to 2 factors. One is when the air warms up, the oceans warm up. And when the ocean water warms up, it expands, thermal expansion. And the average depth in the ocean is about 2 miles. So when it expands, it comes up and reaches higher levels. So that's thermal expansion. So we can tease that out. You can't see it very well, but this green plot is essentially global ocean mass. This is measured by that gray satellite. So thermal mass would not cause that change. For the mass to increase, it means we've had additional water dumped into the ocean, and that's from melting ice. So this is due to melting ice, and then the total is the melting ice and the thermal expansion. And that right now is somewhere on the order of 3.2 millimeters per year. So that's this plot here. So like I say, we're measuring all this with adjacent satellites and the gray satellite, and it's pretty straightforward. Okay. Now, what has changed during this period of time? Well, here's the Industrial Revolution back here, and you can see we started mining coal, started burning coal, started putting carbon emissions into the atmosphere, and then we got, for where coal wasn't enough, and we started producing oil and burning oil, and we started doing natural gas, and actually even developing cement or creating cement also releases some carbon. It's pretty darn tiny by comparison. But still at this point, coal is the biggie, oil second, and gas is third. But those are huge impacts, dumping those into the atmosphere. Okay. Now we can separate out the various effects. If you looked at natural factors only since roughly the late 1800s, that's going to be this zone in green. We would expect the global temperature to vary the way the green is varying, and you can see the sunspot cycles fairly effectively there. But notice the trend line. Essentially, the green is pretty much stable for that whole period over 100 years. It's not really going up. It's varying, but it's not trending up. But if you add in the human factors as well as those natural factors, then you get this purplish shaded region. And if you look at the actual observations that are being collected, it's the black line, and it fits pretty darn well within the line that is explained by, or within the range that's explained by natural and human factors. Okay, this one is much of the same, although I wanted to show you from the mid-1900s, these are decades showing the basically the change in temperature. And you can see every decade it's getting hotter and hotter and hotter. And this is another indicator is heavy precipitation. And again, you can see heavy precipitation patterns more and more and more and more. So another indicator of climate change is, like I say, extreme precipitation events and things of that nature. Okay, go to the next one. So the greenhouse effect, basically greenhouse gases and the greenhouse effect, is the primary thing driving the system in recent years. And what this means is the sun puts energy toward the Earth. It comes to the Earth as in the visible spectrum, okay, short wavelength. Then it warms up the surface and then radiates back out as infrared, long range, and can't make it through the blanket that these gases provide. It can't make as much of it out. So that's the greenhouse effect. More energy comes in, they can radiate back out, so it's out of balance, and it continues to build up that heat. Okay. Now, if you look at all the components and try to account for everything, this is what they generally look like. Here are the greenhouse gases: carbon dioxide, methane, nitrogen oxides, and halocarbons. And then we got some ozone in there. The albedo effect's actually the other way around. And then aerosols are the other way around. Those actually are reducing the amount of energy coming in. Basically, they're reflecting it before it can come in. But when you magnify or put all these together and look at the magnitude all together, you get this huge positive bar here that is showing the radiative forcing is essentially a warming. This is basically what accounts for the warming that we're seeing and that we're measuring. Okay. Now we also run lots of models. Models are a good tool to look at the sensitivity of variables. The global climate model is extremely complex, but they still are not perfect. And that's why basically what I've showed you thus far is not based on models. It was based on measurements and samples and and so forth. When we do look at the models and look at what happens, the various trend lines vary depending on what assumptions we make in terms of what we're going to do about this. Are we going to reduce our emissions and and so forth? And the various scenarios that we can anticipate, we can run those in models and see what the effect is. But if you look at where we are today, no matter what happens, it's going up from here. Even if we basically stop doing what we're doing today, it's still going to go up. But hopefully it could go up and level off at some more reasonable level. But if we keep doing what we're doing, we're on a pretty steep trend line where we're going to see huge increases in temperature. And not just temperature, there's a lot of impacts that we need to think about. Okay, Ted? So what are the effects of climate change? There are lots of them, and I'm just sort of rattled all these off when I was putting this talk together. There's lots and lots of things that this is caused by. And of course I started with atmospheric temperature rise. Okay, well what does that actually mean for us? Well, it also contributes to sea level rise by thermal expansion, like I mentioned, as well as melting glaciers and ice sheets. Warming the oceans, which affects weather, climate, has ecological impacts. The retreat of, melting of Arctic ice, which has, I say, political impacts, because as the Arctic melts, all of a sudden we have transportation corridor across the Arctic. The military is very concerned. If you talk to folks in the Pentagon, climate change is their #1 problem they're trying to deal with. Because they see once that ice melts during the summer up there, all of a sudden they have new pathways to attack us and so forth that they have to put defenses in place for and so forth. And then they also have mineral resources in the Arctic. People will be scrambling for those. Whose are they? Who's going to get to those? You know, so there's all kinds of political ramifications as well as stability. And as well as environmental impacts. And I say cultural because as the ice melts and so forth, it's an impact to the native population up there and, in the northern extremes, the Inuit Indians and so forth. Retreat of glaciers globally, and these also have cultural as well as ecological impact. Frequency and magnitude of extreme weather events. We mentioned that a minute ago, and we're going to see more and more of those. Ocean acidification. As carbon dioxide increases in the atmosphere, the water in the ocean absorbs that carbon dioxide. When carbon dioxide goes into the water, it becomes carbonic acid. It makes the ocean water more acidic. And that's not good for coral reefs. So it has a huge impact on coral reefs and the associated fisheries and other ecological impacts as well. Public health, heat waves, heat stress. We're going to see those kinds of impacts, here in northern Georgia. We might not have to worry directly about sea level rise, but we definitely have to worry about heat waves and heat stress, vector-borne disease. We're already seeing things like dengue fever now in South Florida. We didn't have that a few years back, but now that temperatures are warmer, we're getting tropical diseases and so forth moving farther northward. So we're going to potentially here in Georgia see vector-borne diseases in the future that haven't been an issue in the past. Droughts and floods. Out in the west, we've seen an increase in wildfires. Well, the forecasts essentially from the models are that the southwest U.S. is going to continue to get hotter and drier. We're going to see more extreme wildfires and so forth, as well as water shortages out there. Frequency and intensity of tropical cyclones, so hurricanes. We're going to see more and more hurricanes. As the ocean warms up, that's the energy that feeds the hurricanes. We're going to see stronger and more frequent hurricanes.
Mr. Smoot,
yeah.
What I don't see up there is the turbulence from the airlines, and that what they're seeing is more and more of that, and they're predicting that we're not going to, that your flight from here to New York City is not going to be fun anymore because of the climate change.
Well, that's because of the heating of the surface and the thermals and so forth. Right. Yeah.
But that needs to be included in there from now on.
So ecosystem impacts, temperature, water, and the timing of the impacts. Essentially, spring is coming earlier. Plants are coming out earlier. That's going to affect the ecosystems that are connected to that, And if we have less snowpack and earlier stream flow from the melting of the snowpack, that's going to affect the ecosystems downstream that are relying on that water. So there's all kinds of other impacts that you might see. Agricultural impacts. Obviously, as temperatures change and the timing changes, that's going to impact farmers and so forth. Water resource impacts, we expect to see those in Georgia. The quantity and timing of the water might be an impact. Impacts to transportation. You've already seen some of the impacts to air when we've had the extreme heat effect that we had out in Arizona where they couldn't fly planes because the air wasn't dense enough to hold the planes up, so they couldn't fly the planes. We're going to see more stuff like that in roads and rail and shipping in the coastal areas. We're going to see a lot of that as well. Infrastructure displacement and protection. So along the coastline, as we have increases in sea level, it's going to displace the infrastructure. We're going to have to move stuff, highways, railroads, the ports and so forth. All of those would be underwater. We'll have to move that stuff. Did you have a question?
Yeah, I was just curious, in the climate models and in these predictions, are you, do you know if they're applying very much AI to determine the timeframes?
Well, I mean, at this point, the time frames are dependent on a lot of the assumptions going into the models. Right. So essentially, what typically is done is you put error bars on these. Some things have bigger error bars than others. And then how you use it is dependent on what you're going to try to do with it. I'll tell you a little bit more about that in an adaptation plan here in a minute. And then human displacement and migration. If you look at the population around the world, there's a lot of folks living right near the coastline. They're going to be impacted. People like in Bangladesh, an incredible population at very low altitude. What's going to happen to those folks? We don't have to look that far. We can look to Florida. We can look to coastal Georgia and see that too. Or look to New Orleans. As a matter of fact, New Orleans, half of the city of New Orleans is below sea level already. Pretty scary thought. Miami Beach, downtown Miami Beach is at elevation 6. Or excuse me, Miami is 6. Miami Beach is 4. Yeah, I mean, it's incredible. And so you put a high tide on top of that, and then a storm surge from a moderate hurricane, and you're underwater. You know, so there's going to be a lot of impacts that we need to be thinking about, planning for, and so forth. You can go ahead to the next one. Okay, so let me, since we're running a little bit short on time, I had some regional effects. These are from the National Climate Assessment that was just recently done. And in the Southeast, the primary things that they identified in that assessment was that sea level rise poses widespread and continuing threats to the region's, not just environment, but also the economy. And extreme heat will affect health, energy, agriculture, and more. And decreased water availability will have economic and environmental impacts. This is what's going to happen in the Southeast U.S. based on what the National Climate Assessment just came up with based on their models and data. Okay, go ahead and you can jump to, yeah, these are the other areas. Okay, so path forward, what do we do? Well, I like to think of it in 4 categories primarily. We need to improve our understanding of climate change science. We need to know more and more of the science behind this so we can do a better job. We need to know more about the impacts, understand what those impacts are going to be and how to predict those impacts. We need to understand how to adapt to what's coming. And we also need to look at mitigation. What can we do to mitigate climate change? Examples would be, how do we reduce greenhouse gas emissions? Things like carbon capture, storage, reforestation programs, modifying albedo, which might mean instead of roofing with black roofing material, put white so it's more reflective. I mean, all kinds of little things that can be done. Also, it's good to think that climate change is a global issue, so we need unified solutions at the individual, community, state, federal, and international levels. It is a global problem, so we need to be working on this globally, not just locally. And I put here that adaptive management is a process that I think could apply to this as a complex issue. It's the kind of management tools that, as an example, when I was involved with the Everglades restoration, when I was with the U.S. Geological Survey, also a very, very complex ecosystem, trying to figure out what we could do and what the impacts would be of those actions, very difficult. So we would take our best models, our best information, and we would come up with a plan, and then we would put it in place, and then we would monitor what's happening and then modify our plan as time goes on and we learn more. That's adaptive management. You can go to the next one. Here's kind of the adaptive management cycle that I'm talking about. We plan first, then we do something, then we evaluate, we learn, make adjustments, and then continue to plan, do, and evaluate. So it's a continual process, and that's what I think would work best for climate change. Since it is such a complex issue, we don't have all the answers today. I think we have enough answers to act, but we're going to continue to have to evaluate and modify, as time goes on. Now here's an example of a community that's progressive. This is New York City. New York City this was probably like 8 or 9 years ago, they worked with NASA to put out this climate risk information publication. They formed a panel, they had local participation, all their politicians were on board. They built this plan, they all adopted it, they all worked forward. They basically projected out to the year 2100 what would happen based on the models. They took that information, and this is one of the products that they generated, which was basically what does sea level rise mean over this horizon, and they showed the areas that were going to be inundated. They've used that to factor into their building plans, their zoning requirements, on and on. So they're not building in areas now that are impacted. And if you are building something, you're going to be building anticipating the temperature is going to be a whole lot hotter than today. So you're going to have more insulation, you're going to have reflective building materials. You're not going to build infrastructure, that's going to be in harm's way when sea level rises. New York is very, very progressive, and they're totally on board with this. It's a great example of what you can do when people are willing to work together. And like I say, NASA went on and basically developed, well, it turns out that we have one of our climate research facilities partnered with Columbia University in Manhattan. So we had folks there that were interested in working on this issue with the local folks there as well. But this is a great model for what could be done with all kinds of communities. I would think that Tampa Bay ought to do one of these, and, and so forth. But anyway, most of you probably are aware in Florida they can't even talk about climate change. So currently it's a problem down there, even though they have probably more at risk than any of the rest of us. But at some point, hopefully, they'll get the message. But this is a good example, like I say, of an adaptation planning process and so forth that's worked well. And that's about it. I don't